Dr. Orkunbaycek here, and today we are going to talk about another discrete probability distribution, which is Poisson distribution, and we are going to talk about how we can identify if we have a Poisson distribution, and we are going to look at a numerical example and learn how we can use Microsoft Excel to solve Poisson distribution questions. So to briefly summarize what a Poisson distribution is, in this distribution, we are interested in the number of events that can occur in a given interval of time or space. So we are looking at a time interval, and we are looking at the number of events that can occur within this time interval or given space. An example of a Poisson distribution could be to look at the number of customers arriving in a store in the next 30 minutes. So in this case, we have number of events that can occur. So the number of events that can occur is number of customers arriving to the store, and the time interval is 30 minutes. So we have a time interval and we have the number of events that are occurring in this time interval, so we can model this as a Poisson distribution. We need to satisfy two conditions to be able to model a problem as a Poisson distribution. And those conditions are that, first, the probability of occurrence is the same for any two equal time intervals. So if you have two equal time intervals, the probability of occurrence is the same in both of these time intervals. So if 10 people are coming in 30 minutes on average based on our data, past data, the probability of occurrence shouldn't change from 11 to 11:30 versus 12 to 12:30. Okay, so the probability of occurrence should be the same for both of these time intervals because they are equal. And the second condition is that the probability of occurrence in one time interval does not affect the probability of occurrence in another time interval. So this is the statistical independence, that one probability occurrence in one time interval has nothing to do with the other probability of occurrence in another time interval. So these two conditions must be satisfied to be able to talk about a Poisson distribution. Again, the two key parts of a Poisson distribution will be the number of events that occur in a given time interval. So you have to have a time interval and you need to be looking at the number of occurrences. So I have a numerical example here. In this example, on average, we know that 20.3 customers arrive at our clothing store every hour. So every hour or every 60 minutes, 20.3 customers arrive at our store. We define a random variable x, which is the number of customers arriving in any hour. Part A, what is the probability that exactly 15 customers will arrive in the next hour? Okay, so similar to other examples from other videos, such as binomial distribution, if we are using Excel functions, we will need to answer a question, which is that, is this a cumulative probability or not? So the keyword here again is exactly. If we say exactly a certain number of customers, or similar examples like this, if we use the keyword exactly, or if we mean exactly, then that is not a cumulative probability. Okay? So in this case, we need to answer a few questions here to be able to complete this part. So in Poisson distribution, our parameter is lambda, and lambda represents the mean or the expected value. So in this case, the question gives us what this lambda value is, and that is going to be 20.3. Okay? I am interested in calculating the probability that exactly 15 customers will arrive in the next hour. So my X value that I'm interested in is 15. And then I'm going to type what is the probability that I'm interested in. And that will be X equals 15, because the question is asking me to calculate exactly 15 customers. So to calculate this, I'm going to use the Excel function, which is Poisson.dist. And as soon as you type this, you are going to see that you will need to enter X, mean, and cumulative. So I already put this information on my template. I know X is 15, which is in C14. So I pulled that value from that cell. And the mean is 20.3, which is given in the problem statement. And like I said earlier, I need to answer if this is a cumulative probability or not. And based on the problem description, I'm looking at exactly 15, which means that this is not cumulative. So I'm going to respond as false, and that will give me the answer that I'm looking for, which is 0.047. Okay, so this is part B. Part A. In part B, the question is, what is the probability that at most 17 customers will arrive in the next hour? So now we are talking about another keyword, which is at most. So here's the thing. When I say at most 17, you need to ask yourself, does this include 17? Yes. Does this include 16 customers? Yes. How about 15, 14, 13, 12, all the way down to 0? Are they all included? Yes. So if you include everything, including and up to 17, then you are looking at a cumulative probability. Okay, so keep that in mind, because that will be important. First of all, I need to put what my lambda value is, which is 20.3 per hour. It didn't change. X value in this case is 17, because we are going to look at most 17, and the probability that I am going to calculate is X less than or equal to 17, and my function is Poisson.dist. Again, I need to put in what X, mean, and cumulative answers are. X is 17, as I already put it in my template. The mean is 20.3. And like I said, this is a cumulative probability because it says at most, which includes 17, 16, 15, and so on. So I'm going to answer this question as true, which will give me the answer of 0.274. Okay? So question C. What is the probability that at least 18 customers will arrive in the next hour? So here is, again, if you watched my binomial distribution video, we are going to use the same approach, because if we need to find at least 18, all I need to find is what is the probability that at most 17 customers will arrive in the next hour, which I already know what the answer is from part B, which is 0.274. And if I subtract this probability from 1, that will give me the answer that I am looking for. Okay, so I'm going to do 1 minus 0.274. And again, the idea is that we are looking at all the possibilities, and the sum of all those possibilities will give me 1 by the rule of probability. And I already know the probability that at most 17 customers will arrive in the next hour from part B. And if I subtract that probability from 1, that will give me the probability that at least 18 customers will arrive in the next hour. Part D. What is the probability that exactly 15 customers will arrive in the next 30 minutes? So here's a tricky question. Poisson distribution can be scaled. So it has this property that it can be scaled. What that means is, for example, I have a website and 10 people click on my website every 10 minutes. And if I want to find the number of people that click on my website every 20 minutes, all I need to do is to multiply 10 by 2. So the idea is if 10 people click on my website every 10 minutes, 20 people will click on my website every 20 minutes. This is the scalability property of Poisson distribution. So we are going to use this idea in answering this question. So my lambda value is 20.3 per hour. But this question is asking 30 minutes time interval. So my time interval is 30 minutes rather than 60 minutes. So to be able to calculate my new lambda value, all I need to do is to divide 20.3 by 2 because my time interval is now 30 instead of 60. So 60 divided by 30 is 2. That's why I'm dividing 20.3 by 2. And that will give me my new lambda value. So I scaled my original lambda value based on my new time interval. All right. So we are going to follow the same approach as part A here. Nothing special. So X value is 15 as we are looking at exactly 15 customers. So probability X equals 15 is what I am looking for. So ask yourself now, is this cumulative or not? You already know what the answer is, and the answer will be that it is not cumulative. So we are going to use our function Poisson.dist. So X is 15, the mean is 10.15, and the answer to cumulative is false because the keyword exactly appears here, which means that this is not a cumulative distribution. So the answer to that is 0.037, and the only question that we have left is part E, which is that what is the expected number of customer arrivals in the next hour? The answer to this question is simple because lambda gives me the expected value or the mean arrival rate. Therefore, the answer to this question is 20.3. So the expected number of customers in the next hour is 20.3, which is my lambda value. All right. So in this video, we talked about how we can identify a Poisson distribution and how we can answer a Poisson distribution question using Microsoft Excel. All right, so thank you so much for watching this video, and I will see you in the next one.